So in this video we'll solve one exercise from 4.7 in the book. Okay, that is question number 3. Okay, we are going to solve this exercise. So for this we have to remember the definition of S0 of an analytic function. Okay, so you see the section 3.1 which is already given, which we have already discussed in our class. So 3.1 we have this definition. So it is given that if f is an analytic function and a belongs to G such that f of a is equal to 0, okay, then a is a 0 of f, then we say that a is a 0 of f of multiplicity, say m is greater than or equal to 1. If there exists another analytic function g to c, which is small g, say g to c, such that f of z can be written as z minus a to the power m into gz. Okay, f of z can be written as z minus a to the power m into gz, such that ga is not equal to 0. Then we say that a is a 0 of multiplicity m. Okay, a is a 0 of multiplicity m. So this type of concepts are there, 0 of multiplicity m in terms of polynomial. Okay, so same definition, but here the function is analytic function. Okay, f is an analytic function. Then we say that a is a 0 of multiplicity m if we can have another analytic function g such that f of z can be written as z minus a to the power m gz, whereas ga is not equal to 0. Okay, so this is the definition of 0 of multiplicity m. And we need another actually result. So this is actually from 2.9 in the book. You can see page number 37, 2.9. So this is the result. We have the converse part, we established the converse part, but this result already in this 2.9. So if a power series is given with this radius of convergence, okay, then automatically the power series, that is fz, is analytic in this open ball, okay, with radius r and center at a. Okay, so power series is given with radius r is greater than 0, then automatically that power series is analytic in this. Okay, so every power series is actually an analytic function on the corresponding actually the open ball, where a is the center of the open ball and r is the radius. So this is the result we are going to use in our exercise actually to solve the exercise. So what is the question? The question is actually this question is also familiar in terms of polynomial. You see, f is analytic in this open ball BAR, and suppose that f of a is equal to 0. Okay, then so that a is a 0 of multiplicity m if and only if all these derivatives are equal to 0 other than the mth derivative. Okay, other than the mth derivative. This type of results are there in terms of polynomial, if f is a polynomial. Okay, so we have to establish this concept of 0 in terms of f is an analytic function. Okay, so if and only part, so this is a a is a 0 of multiplicity m if and only this condition is satisfied. Okay, so first you assume that, say, suppose all these derivative equal to 0 other than this mth derivative. Okay, all these derivative 0, that is f to the power n of this nth derivative of a is equal to 0 for all n is equal to 1, 2, 3 up to m minus 1. And of course f of a is also 0 because it is given f of a. For n is equal to 0, we can assume that f of a n is equal to 0. Okay, so f of m is not equal to 0. To show that a is a 0 of multiplicity m, so a is a 0 of multiplicity m means you have to show that f of z is equal to z minus a to the power m into gz. You have to find out what is that gz. Okay, what is that gz? So it is given that f is an analytic function. So therefore, for analytic function, for every analytic function, we have this power series representation. For every analytic function, we have this power series representation. Okay, Analytic function is this open set B center open ball B centered at a radius r. Then fz can be written in this power series form, okay, where mod of z minus a is less than r. Okay, so within that open ball we have this power series representation, and ak is equal to, this is our ak, k derivative of a divided by factorial k, that is the coefficient. These are the coefficient. For every analytic function we have this power series representation. For every analytic function we have the power series representation, and we have this coefficient ak in this way. Okay, coefficient ak, you can find out the coefficient ak in this way. So this result we have already established this result. Okay, so this is the result actually. Okay, so f is analytic function. This is the result. You see, the result is actually 2.8. This is the result, 2.8. Okay, as this is analytic function, then fz this, okay, where this series of radius n greater than 1, okay, greater than 1, and we have established this f is we have established this result, analytic function. Then this, we have this power series representation. Okay, so this is actually 2.8. okay, 2.8. so from the 2.8 you can see 2.8, this is from 73 page number. Okay, 2.8 page number 73, page number 73. Okay, so since f is analytic in BAR, therefore we have this power series representation of f. So this is the power series representation of f, where mod of z minus a is less than r, that is on this open ball. Okay, every value is n, where ak is equal to, this is ak. Okay, ak this. So substitute the value of ak, this is ak. Now you take this z minus a to the power m, take this z minus a to the power m term from here. Okay, z minus a to the power m term from here. So then this will be actually z minus a to the power k minus m. Okay, now this part, if I consider this part, this is equal to gz. Since from this is gz, then you can see g of a is not equal to 0. G of a is not equal to 0, because g of a is equal to 0 means all this part, all terms are 0 in this summation sign, all terms are 0. But if I consider k is equal to m, then there is no z minus a term, that is k is equal to m, that is fm a divided by factorial m. So fm a is not equal to 0. It is given that fm a is not equal to 0. Okay, so since as fm of a is not equal to 0, therefore g a is not equal to 0. Okay, this is not equal to 0. So this is an, again g is an analytic function, because we have this power series representation for g. So this is from again 2.9. So 2.9 means that 2.9, the previous one 2.9. Okay, so you see this 2.9. so from this, since z minus a is less than r, z minus mod of z minus a is less than r, therefore gz is also an analytic function in this open ball BAR. So you observe ga is not equal to 0 and z is analytic function, that is we have this analytic function, this is the analytic function, such that f of z is nothing but z minus a to the power m into gz. Okay, into gz. Therefore a is a 0 of multiplicity m. This is from the definition. Okay, this is from the definition. This is the first part. So conversely, we assume that if f of a a is a 0 of multiplicity m, suppose that a is a 0 of multiplicity m is greater than or equal to 1, so we have to show that all these derivatives are equal to 0 at a other than the mth derivative. Okay, that is your intention. So by definition, there exists an analytic function in this open ball, because the function is defined in this open ball, so such that this condition is satisfied. Now you find out the derivative. So you can our objective is to find out the nth derivative of this fz. So you can see fz is, this is the fz product of two function. Okay, I have found out a derivative of first derivative, second derivative, third derivative. Okay, third derivative. So we just verify it, then you see this is third derivative can be written in this way. Similarly for the second derivative can be written k from 0 to 2, this is 2 and this is 2, this is 2, something like that. So in general, you can write down the nth derivative can be written in this way. This is the nth derivative. Okay, nth derivative is this. Okay, so this is nth derivative. Therefore, you can see if I substitute z equal to a in this nth derivative, then this is equal to 0. Fn of a is equal to 0 for m minus n minus k is greater than 0. Okay, m minus, that is its term contains this z minus a in this summation sign. Its term contains z minus a. If m minus n minus k is greater than 0, then its term contains this z minus a. Okay, so in this case this is equal to 0. Okay, and for n this is not equal to 0. If this is equal to 0, if this is equal to 0 and this part is equal to 0, that is we have only this part with the where we have only this part. So this is, if this part is equal to 0, this part equal to 0, then there is no term z minus a actually. So since there is no term z minus a, then automatically fn of a is not equal to 0. Okay, fn of a is not equal to 0. Okay, so fn of a, in that case fn of a is not equal to 0. Fn of a is not equal to 0. So so if I consider k is equal to 0 and m is equal to n, so this m is an, actually m is an you can, this is the generalized formula for nth derivative of fz. This is m is a particular derivative of fz. So if I consider m is equal to n, then this is true for every value of n. So therefore for m is equal to n, we can have only one term. Okay, k is equal to 0 only. K is equal to 0. M is equal to n. M is equal to n. So for this observation, we have this is not equal to 0. So if I substitute m is equal to n, just put m is equal to n, we have only one term. This is factorial m, and m is equal to n. K is equal to 0. This part is equal to, this part equal to 1. This part also equal to 1. This is factorial m. Okay, k is equal to, this is then this is k is equal to 0, that is z0, za, only za. This is only za. K is equal to 0. This is the first term. Okay, first term. Okay, but za is not equal to 0. This is factorial m. Okay, factorial m. So for a convenience, you can check for this m is equal to 3. You can observe for m is equal to 3. Okay, if I consider m is equal to 3, if this m is equal to third derivative, you see the third derivative, m is equal to 3, then this term does not contains, okay, this term does not contain z minus a. Okay, therefore this is not equal to 0. Okay, if the multiplicity of a is equal to 3, okay, suppose a is a 0 of multiplicity 3, then you can observe this third derivative. Okay, so this term is not equal to 0 in this case. So this will give the required result actually. Okay, so mth derivative a is not equal to 0, but other derivative up to m minus 1. Okay, but therefore this is equal to 0. This is 0. Okay, 0, m minus 1 equal to 0 for from here. This is equal to 0, and from 1 to up to m minus 1 you can observe, and from 1 to up to m minus 1, which is actually greater than 0. Okay, greater than 0. So this is the required result, hence the result.